Hello, my name is Jiawen Hu. I'm currently a fifth-year PhD student in CPAS, and my advisor is Dr. Rolando Burgos. My research interests include magnetic integration, high switching frequency converter design with a focus on EMI mitigation, and enhanced gate driver technologies for silicon carbide MOSFETs. In this video, I'll be talking about the enhanced gate driver design for silicon carbide-based generator rectifier units for airborne applications. AC-DC converters or rectifiers, also known as generator rectifier units, played a leading role in airborne systems. Over the past years, the aerospace industry has sought to develop generator rectifier units, GRU for short, featuring high efficiency, high power quality, and high power density, all in an effort to improve their performance and reduce the size and weight. However, the aforementioned effort has been limited thus far by the power processing capability of silicon power semiconductors. In these days, wide bandgap power semiconductors have emerged increasingly as an alternative in airborne applications. Bottom left corner shows the silicon carbide MOSFET module developed by General Electric with the use of their GE proprietary power overlay technology. Exceedingly low parasitic inductance value of less than 5 nH is achieved. Moreover, recent qualification tests have also demonstrated a thermal cycling and power cycling performance beyond that of state-of-the-art wirebond modules. The target in this work is to operate the whole unit at 50,000 feet, which brings installation challenge to the GRU. As the altitude increases, the air pressure reduces, which decreases the insulation strength. On the left shows the pattern curve at different altitudes. It illustrates that the breakdown voltage decreases significantly at high altitude. Therefore, the insulation strength has to be increased correspondingly. However, few standards provide altitude correction factor for 50,000 feet. IEC 60664 is the only standard that provides an altitude correction factor of 6.7, which might be overdesigned and reduce the power density. To this end, an insulation coordination is designed. Breakdown electric field is calculated based on pattern curve. It shows that the breakdown electric field is infinitely close to 600 volts per millimeter. 50 margin is added to ensure safe operation. The maximum electric field in the air should not exceed 300 volts per millimeter. The gate driver structure is shown on the left. Rogowski's switch current sensor is implemented to improve the protection speed and eliminates the need for external current sensors. The equivalent circuit and the functional diagram of the Rogowski switch current sensor is shown on the right. To reduce the electric field in the air, E-field control methodology is used in the gate driver layout design. As labeled on the top view of the gate driver model, the worst case exists in the interface area between high side and low side gate driver circuitry. Internal copper planes were designed to shift the peak electric field from the air to the FR4 materials. As a result, the electric field along the gate driver surface in the air is controlled below 300 volts per millimeter. Here shows the gate driver assembly. These cutouts are for the 3 terminals, which are positive DC, negative DC, and AC terminal respectively. Rogowski coils are formed by PCB trays and vias, which are fully embedded in the gate driver PCB to provide sufficient insulation strength. On the left are the switch sensor circuitry. The gate driver IC circuitries are in the middle of the board. FPGA and LDOs are located on the right. Here shows the Rogowski coil switch current sensor output and the switch current measured by a commercial current probe. As seen, it successfully matched the switch current, verifying the design of the current sensor. The double pulse test results are shown in this waveform. The bus voltage is 540 volt and the peak switch current is 235 amp. Partial discharging tests were also done in an altitude chamber in SiC-Based. All high voltage and low voltage potential exposed pads are connected for test. Breakdown exists at the edge of the copper tape. The partial discharge inception voltage at 50,000 feet is 617.2 volt, which successfully meets our target. In summary, a gate driver for silicon carbide-based generator rectifier units for airborne applications is designed. Insulation coordination is designed based on passion curve. Electric field control methodology is applied in layout design, and the electric field along the surface in the air is below 300 volts per millimeter, according to 3D FEA simulation. Rogowski coil switch current sensor is implemented and a faster protection is achieved. That's all for today's presentation. Please feel free to reach out by email to me about this research if you have any questions. Thank you all for your attention.